Thank you very much for the invitation to speak today. I'm from the University of Hertfordshire. Two things to know about Hertfordshire, if you're not too well aware of us. Do go and have a look at our website for the Bayfordbury Observatory, a very nice teaching observatory we use for our degrees. And from a space perspective, of course, we date back to the Blue Streak rocket developed there in the late 1950s. And the university itself grew out of the old de Havilland Technical College. I'm going to be talking about how you put a sort of space pathway within a physics or astrophysics degree. I'm very happy to answer questions about astrophysics or physics degrees. Specifically, this would be what the additional core modules would be for someone studying space science within a physics. I'm going to concentrate mainly on two modules within this. You see some of these modules are shared with engineers doing a space technology portions of their engineering degrees. I'll only talk about a couple of modules in here, just to show how sort of a slight physics slant on modules which you'd also, of course, find with engineering degrees. Some themes I'm going to, which run throughout these things are use of dimensional analysis, problem-based learning, which you've heard about before today. I was lucky to have a space scientist actually doing a PhD with us in astrophysics purely for interest, and was in between jobs in the space industry, who gave me a lot of help in making sure the students were able to answer questions, not only technically at a decent technical level, but around the table. You know, how long is this going to take? At what temperature is this going to rise? So we based a lot of our little work on small, simple calculations as well as more complicated analytical ones. There's group work involved in designing missions, etc. And there's not too much pressure on us from accreditation, which from the Institute of Physics is basically based upon a core of physics. We're able to develop that in the space science thing, so things that you might not find within the core will occur in the curriculum of these modules I'm discussing. And also we can discuss some beautiful solvable toy models. It's possible to take a thermos flask and linearize the equations for the early drop in the temperature of that thermos flask and see if you can get a decent scaling law. That's to say, if you buy a thermos flask with a capacity 3 times as large as a smaller one, what's the length of time before it gets down to a drinkable temperature? Which I don't know if you know what the drinkable temperature of tea or coffee is. I didn't know when I did this problem, but apparently it's about 60 degrees C. That's where you should go down to. So that's the Royal Institute of Chemistry, I think, recommended temperature for drinking. This is a Trumpian world of survivalism, and so I like our students to regard the space science that they learn as being grounded actually in things that we've worried about for a very long time. All these pictures come from one of my favourite books as a child, which was the Stone Age, Ladybird book, Stone Age in Britain. And but this is space science, as you can probably gather. This is environment, tools and instrumentation, power. What we've got over here is thermal control, structure, and communications. It's all there, ready to be developed into a much more highly technological subject as we go through. I'm just going to show a few little pages for workshops that I do, just to indicate some curriculum content that we're able to go, as I say, above and beyond the IOP core. So we'll be looking at those themes. We've done some pictures before. So the environment here, this is a workshop based on a Maven research paper, and so they go beyond their core electromagnetism, looking at magnetospheres, neutral sheets, ram pressure. I'm always very sad that fluid dynamics isn't in the physics core. I think it's a historical thing. There weren't many fluid dynamicists in physics departments. There's plenty of engineering. But it's a really lovely thing to actually teach within the physics curriculum. There are obviously space debris. You can do lots of lovely physical things, about the energetics of these things. But in the physical terms, I'll come very shortly to an example where we can look at it in terms of dynamical orbits, etc., which is a rather nice thing to do. And in terms of developing their skills from optics, they can take obviously spacecraft images and analyze them. How big are these objects? Contrast atmospheric models they may be seeing in these images. The rolling motion, they might see an asteroid, how much little particles to roll down a slope. Those kind of questions are rather interesting. So image-based analysis is something that's rather nice way of teaching for those people who like to visualize things. This is another environmental one, a rather nice one based around Enceladus, one of the hydrothermal plumes from Enceladus. And again, it will start with maybe some dimensional analysis, so working out the tidal generation power, just using dimensions to begin with, and then slightly more sophisticatedly looking at what would a spacecraft would experience as it flew through one of these plumes. So you've got a rather complicated looking density function here by one of these plumes, and you've got to work out if you're particular trajectory through this atmosphere, what you would experience, not as a function of position, but as a function of time. Rather interesting thing to do. So it's rather nice to generate first of all, some contours for these plumes, and then to generate the experience, the Lagrangian experiences you travel through one of those plumes, the density experience during that trip. And then we can develop some extra topics here, kinetic theory, maybe first mention of Mach number, tidal heating, radiative heat flux from a body which has been tidally excited. Some of the exercises we do would look not out of place, almost certainly in an engineering space science module as well. So things like solar cells, of course you're going to find those in the engineering side of things. For our students in physics, it's rather unusual for them to actually access a data sheet. So just a solar cell data sheet and then invent their own solar panel based upon that data sheet, something they wouldn't ordinarily meet, much more common than the engineering side of things. Heat transfer models, again, will be nodal analysis that you'd find in an engineering approach, but for the physicists, they won't necessarily meet thermal conduction beyond, heat conduction through a surface or through a pipe, not multi-component heat conduction through a series of different media, for instance. That would be new to them. And just so the little power budget for a satellite brings in things which they wouldn't ordinarily meet in simple orbital analysis or simple thermal analysis of objects irradiated by the sun. They'll know about how to calculate the surface temperature of planets, etc. But it's a more complicated thing, as you know, when satellites are spinning and they're going into eclipse, and their orientation with respect to both the planet and the sun are changing over time. So you probably get the impression a lot of this thing is done by teaching by workshop. The workshops aren't short things, short pithy questions. They're quite developed. These are typically 4, 5, 6, 7 pages long. Here's a space debris one where we can again see a little bit of dimensional analysis, just working out how the drag force depends on density and velocity to start with, and then slowly building up to a nice sort of simple toy model of the space debris decay. So that's to say where all these particles are, and then given their experience in drag, where they will end up over time. So you can now introduce a sort of kinetic theory of space debris. You've got all these little objects in space which are slowly evolving orbits, and there'll be a local number density of those objects which evolves both in space and time. And you can calculate a nice little kinetic model with relatively simple assumptions. And again, very similar things like you find in an engineering module, an RF link budget. That's new to a physicist, but we'd follow very much the same principles as you would in an engineering question of that type. In terms of thermal control, I suppose the engineering side of things would probably look more at what was going on within a spacecraft. We're also rather interested in picking up topics from the last talk on thermal control about surviving beneath the planetary surface, so what the temperature will be as a function of time below the planetary surface, which allows you again to do some simple scaling and then some rather slightly more sophisticated modelling, where you can calculate the temperature on the surface as a function of time. That temperature, of course, may be varying because of the change in the surface temperature over time, and of course as a function of distance below the surface. So you'll see both a diminution in the amplitude of that temperature variation, which might allow you to make a base which has a nice comfortable range of temperatures over a typical day, and also a time lag in that variation because of the distance you are below the surface. And motivated by the interest in saving moles, of course, how deep does a mole have to burrow below the surface to survive a fire on the surface of the Earth? Structure, it's always rather hard, I think, to have interesting structure questions. This is a slightly artificial one. in which we look at a radio telescope. These are the parabolic receiver here, the parabolic dish here, and the receiver here suspended over this crater, probably being held by chains rather than by beams. So I've rather artificially created a model one where the receiver is held by beams just so they can do a little structural calculation on beams. Again, it isn't really in the core of the physics curriculum. There might be some mention of it, but very little actually on stress and strain. Lots of particle dynamics within the core curriculum in physics, but not so much continuum mechanics. And space elevators are a really nice topic to do, where they can develop knowledge of gravitational forces as a function of altitude, which of course is definitely going to be part of the core. But here, of course, we've got additional forces within your space elevator caused by the stress in your, whatever it is, your carbon rod structure, which extends above the surface of the Earth and is used in principle as a quick means of getting to altitude. So this space elevator is above the Earth's surface and essentially co-rotating with the Earth. And of course, objects above the Earth's surface want to rotate at different rates naturally, and so there's going to be a stress within that elevator, which is relatively easy to model analytically and get some nice results out of. The space dynamics module, which I will very briefly mention, is a total problem-based module, no lectures at all, which you might think is terrifying for students. It's very good for students, actually. So they all walk into a room not dissimilar to this with computers, and straight away they essentially have a little booklet, online booklet now I suppose, where they work their way through workbook exercises like this. The whole module is essentially maybe 30 exercises like this, increasing in difficulty as they get from beginning to end. They're helped along a lot at the start and less as time goes on. And toward the end, the final questions are very much ones which can be answered in many different ways. So we also accept different programming languages, so they can use Python or MATLAB or whatever for the final set of questions as they wish. This one's to do with the spin stability of the space station. So they create a model space station with such point masses located in Euclidean positions, work out the inertia tensor, and then figure out the spin stability of that space station by its principal axis, which you can modify, of course, for satellites or for irregular asteroids. Orbital dynamics, they'll go to injection orbits, transfer orbits, etc. They can have slightly more interesting ones, maybe, where you don't do classical home and transfer orbits, which are nice and analytical, easy to work out, but more realistic fast transfer orbits, such as a trip to the moon. And again, you'll have to work out the locations of the spacecraft and the moon target refer as a function of time, and figure out the continuously variation distance between the spacecraft and the moon over time, and the appearance of the moon, the angle between the spacecraft and the moon over time. And also, again, interesting things to do. Ion rockets, you can put some propulsion into this thing. This is a rocket which is propelled by ion rockets early on. Eventually, the ion rockets turn off and it's on a free elliptical trajectory. And so there's an optimization issue there. You can decide how long you're going to burn your ion rockets for, and how quickly you can arrive at a specific point at which you're going to make an interception. Say, we were interested in Oumuamua, those fascinating asteroids which have come from outside the solar system, and how easy it would be to rendezvous with one of those. And this one is showing the volcanic plumes on Io, a little exercise really in modelling in two frames, in a rotating frame, rotating with Io, and in a non-rotating frame looked at from the point of view of an inertial frame that was outside of Io, just really getting them experienced in evolving equations of motion in non-inertial frames, and Coriolis force, etc., etc. So I'll just finish by making a very small plug for an additional department within our university. This is the model design department, which is for many years has been producing models for the film industry. It's an undergraduate degree, and so you can, should you so wish, and several academics over the years have commissioned models of their own spacecraft, which the Cassini spacecraft that we made a lovely little Cassini model for John Zarnecki. You can have a little model made for you, maybe as part of a student project. They're much cheaper to buy than they would be if you got one professionally made without getting a student to make it for you. And the student benefits because they have to make a contextual model as part of their degree. So if anyone's interested, I'll leave these flyers by the coffee and tea if that's all right, and you can just help yourself or get in touch with me afterwards if you don't get those details. And if you need something made, you can just get in touch with the program leader of that course in Sheffield.
Okay, thank you very much.